these things take a bit to load. PowerPoint slides are always like that. So, all right, self-balancing trees. So, so there's a bunch of different. So basically, we learned that binary search trees have a log n search time, but that's on average. Worst case for binary search trees is that they're O of n. And so self-balancing search trees are trees that enforce a log n runtime. And the way that works is that what they do is that they detect whether they're unbalanced or not. Right, so they add or delete a node, check if the addition or deletion makes the tree unbalanced, and then from there they can check whether it's unbalanced. Once it decides if it's unbalanced, it can fix the unbalance in log n time. So the add operation becomes log n plus log n, which is still log n. So there's different ways to do this: AVL trees, red-black trees, 2-3 trees, 2-3-4 trees, and B trees. Let's see. So these are kind of your examples of unbalanced trees that they have, right? I saw one of you gesture that, this is what an unbalanced tree might look like. Add in 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, and so on, right? It's just going to essentially be a linked list with extra steps. Okay. A more realistic example of unbalanced tree is adding the quick brown fox jumps over the lazy dog. This is the tree that would result from adding that sentence. And notice that it is very unbalanced. Every time, and what I mean by that is that every time we make a decision or search for something, every time we go down a edge in the tree, we're only really eliminating one node from our search space. So everything takes O of n time to look up. We're really only, right? If we go here, right, we found our node, but every time we go down, we're really not cutting anything out of our branches. So the way that these are fixed is by using a rebalancing operation called the rotation. And what that does is that it changes the heights of it changes the relative heights of left and right, but it still makes it a binary keeps it a binary search tree. And the way it works is that given your root of a tree or subtree, what you do is that to rotate to the right, you grab your left child's right child, okay? You grab that and then make your left child the root. Okay? So again, what we're going to do is so in clear steps here, which is what you're going to be doing, right? Here's the algorithm for rotation. Remember the value of root.left, right? Set temp is equal to root.left, right? Or root.left, correct? Not right. Okay? It's one of those weird idiosyncrasies of the English language. So set this temporary variable, root.left, and then grab your grandchild, the left's right child, right? Set your left's right child to your left child, okay? Now normally that would do bad things to the tree, but we're holding on to this temporary variable. Okay? Then what we do is that we say, hey, set this node, my former left child, his right child becomes the root. So see how that kind of how those again, let me see this to see how these pointers move around, right? Take your node, move your root's left pointer, move your former left child's right pointer, and now make that former left child the root, right? And notice how this guy is now in a root position, and we just kind of restructure it this way. And what this has done is that, and let's just go back a second to this one, right? Notice what happens here is that the tree is still a binary search tree. because what we're doing is that we're taking this right child, right, and making him, and we're putting it on this guy's left child. No problem there, because this is still less than this guy. So making him a left child, making 15 left child of 20, that still works. And then once we move this guy up, well, everything that's to the right of 10 has always been basically larger than 10. So it maintains that property. That was a bit of a lame explanation, but it's easier to see. And so we'll go into the Wikipedia page on that, but let's see how this works in practice. You have AVL trees, which are, I'm not really sure how to pronounce that name, to be honest. But it's the acronym of their developer's initials. And what it does is it keeps track of the difference in the height of each subtree. And then if it gets out of the range of -1 to +1, it's rotated to be back and balanced. We never really defined balance, by the way. Balance just means that my left subtree and my right subtree don't differ from a height of more than 1, okay? Then my left subtree and my right subtree don't differ from a height of more than 1, and that property is recursive, right? So they're also, my left subtree and right subtree are also balanced if it's a balanced tree. And so what this does is looks to see if things get out of balance, and I'm just again going to blaze through this. And once it detects it out of balance, it does a rotation. And there's different ways of doing it. They have like left-right tree. They have a left-left tree describing imbalance, left-right tree, right-left, and right-right. And then each of those scenarios of how it's going to become unbalanced has a specific way to deal with that, right? Right? If it's left-left, you want to rotate right around the parent. If it's right-left, you do 2 rotations. If it's right-right, you do 1 rotation, and then if it's right-left, you do 2 rotations. So it shows that basically, okay, if we do the quick brown fox, right, then this is a right-left. So it does 1 rotation and then rotates over here. So 2 rotations right there, no worries. And what it does is it just simply rotates things to make them maintain its balance. And the idea here, it ends up being fairly straightforward to do. But, you know, it adds a bit more tedium into doing it. Then there's also the red-black tree, which is Sedgwick is a computer science has done a lot of computer science textbooks. Now this one's pretty good. This one is given out as an assignment a lot of times to build a red-black tree. It's pretty much designed for that. It's a self-balancing binary search tree, and what it does is that it changes the definition of balance slightly. It changes it so that basically balanced only cares about the height of black nodes in the tree. So what you do is that you color nodes and maintain these rules. Everything is either red or black. The root is always black. Red nodes always have black children, and nulls are considered to be black nulls for the purposes of counting. And then the path to the path from the root to any leaf has the same number of black nodes in it. So 1, 2, 1, 2, 1, 2, right? So all the paths have the same number of black nodes. Once that gets out of balance, there are 5 different ways that will be unbalanced. Here we actually have that rare. This is one of those rare things where we care about the uncle node or the aunt node. But basically, we always add a red node, and so what's going to happen is that basically we figure out a way to deal with our. We basically detect an issue, and then we resolve that issue in a specific way, right? Hey, okay, so here it just simply moves that black root down to its children. Right, and so there's just different ways of dealing with each of these scenarios. It has 5 different cases. Each can be resolved by changing colors or by rotations and changing colors. And it ends up being, and anyway, it's fairly it's a fairly, it's not necessarily complicated. Sorry, it's not complex or complicated. It's just boring. It's tedious. There's the word. It's changing all these things is a tedious process. All right. So other trees that we see, let's see. Yeah, I think the add method's like 43 lines long or something. Yeah, if you're making it as concise as possible. Yeah.
Do you always have red nodes initially when you're adding to a red?
Yeah, I believe so. I believe that's the case. All right, so we kind of talked about, I brought up this about last week, 2-3 trees. So it's not specifically a binary tree anymore, but it's still binary search tree. Because you got 2 nodes and 3 nodes. 2 nodes have up to 2 children. 3 nodes have up to 3 children and 2 values in them. So a 3 node contains 2 data fields ordered so that you have you have 2 numbers in it, and then you have basically 3 children. Your left child has all the numbers that are less than both the numbers. Your right child has all the numbers bigger than both the numbers, and your middle child has all the numbers in between.
Like a range.
So yeah, so here's an example. Like notice that 11 and 15, this node will hold everything between those two. So and it's not too much more to add how to do that. Right, if you're looking for 13. 13 is great. It's a 2 node, so you check. 13 is greater than 7. Okay. Hey, 13. Go to the next node. It's the 3 node. Check if it's in between. So, well, first check if you're less than the smallest one. Then check if you're less than the bigger one. If you're less than the smaller one, if you're greater than the smaller one and less than the big one, then guess what? Go down the middle branch, and you found it. So the way it does it is that it's built from the bottom up, not from the top down. So instead of hanging a new node onto the leaf, we insert a new node into a leaf. What does that mean? Well, when we insert 15, we insert it normally, and then because this node is a 2 node, we just jam it in there to make it a 3 node. Okay? Rather than adding it on to the end, we just kind of just jam it in there. Okay?
Can you go back 2 slides?
Yeah.
Or one more? So you have one.
It's an 11.
It's an 11 and it has to be like...
It's 11 and it's just
bigger circle.
PowerPoint just doing its thing. Sorry, my bad.
Sorry, no.
11, 15. Now we insert 17. And because we insert into leaves, we kind of pretend to insert it into this node. But because we can't store 3 values, basically the middle value gets popped up, gets kicked back up to the parent. Right? So we've got 11, 15, 17. And so what we do is that we're like, well, we can't store 3 numbers in here, so we're going to kick the 15 up over to here. And then we're going to split all those numbers up.
Why wouldn't you move the 11 up?
Because you want the middle node to be pushed up so that you can then move so that you can turn it into a 3 node that way. Then insert 5, 10, and 20. And this is where it will get interesting. Once we insert 13, right, okay, what do we have to do?
Kick it up.
We have to kick it up.
But then you have to do it again.
So we kick it up to there.
Oh, that's...
That won't work, right? So we just kind of pretend, though, that it will. And then we got to kick up the middle value again.
Yeah. That's
And then split the remaining values into 2 nodes. So we split the 7 and the... So basically, we split the 7 and the 15 apart.
Oh, and they each get the 2. Okay.
Right? It looks complicated, but it's really not too bad, right? But it basically keeps everything. There's not really any rotations that go on here. You just kick things up. All right. Yeah, bam. All right, and then there's, it was the inspiration for the more general B tree, which is used a whole lot, like as the base for a lot of file systems. B trees, B plus trees, yes.
just back to the beginning of the 2, 3 trees, how do you determine, I guess, in code where you would, which leaf to initially add?
You would search for the place to you would do the normal insertion algorithm looking for an empty.
You do the regular traversal.
Yeah, and then but rather than adding the node to a new leaf, you basically try to insert it into the node, right? So you would go. So here, if I was going to add whoa, I would start the root, go left, go left, go left, and then add whoa to the. Whoa.
Left, right. We're saying left and right. Is it looking at the tree or is it from the view of the tree? You just said it, and I've been now it's backwards.
Oh, I right. Go right. No.
Okay, I didn't.
The right. Don't make it hard.
All right. Judge the tree. That's a maple.
All right. So there's also a 2, 3, 4 tree and the like. Like a B tree looks like this, where it basically has a generalized number of children. Not really going to go into that now, but it's interesting. It was developed for disk storage, and then it can be a bit tricky, but but it's pretty nice.
That's how you address hard drives.
Yeah. So now let's go to today's exercise, which is tree rotation, right? Going back to the beginning. Tree rotation. So I love Wikipedia. I don't know if I've expressed how much I love Wikipedia. And I think this is a huge difference between me and other professors because the vast majority of other professors were not in high school when Wikipedia, initially came out. Yeah, so, for me, whereas they've kind of got this inoculated mistrust because students will copy and paste from Wikipedia. Yeah, well, you won't, but the bad students do. But, for me, it's just a matter of, it's brilliant, especially for computer science stuff, because, people go out of their way to make nice GIFs, right? So this is the way that, so a left rotation and a right rotation, by the way, cancel each other out, which kind of makes sense.
Yeah.
Right? So here, right, and there's basically two things. They use P and Q, or they use lambda, alpha, beta, or something? I don't know. Whatever. It's stupid. They're coming from a mathematics background, and they really should just use the terms that pop up over here. The root and the pivot. The pivot becomes the new root, but you're basically pivoting it up. This graph, I think, is shows it the best, which is what you do is you take the root, move this over here, and you take this guy, make it the. So what you do is you basically take your pivot's right child, your pivot's left child, and now the root becomes the pivot's right child. Okay? Just two moves over there.
There was nothing wrong with the first one, though, right?
Right.
Okay, it's just showing like this.
I prefer. This one uses terms that you'll probably use when you're coding, which is a root and pivot. Now, the one thing that that we need to do for our trees, for when you implement this, is that our methods need to look like this. Our methods really need to look like this, which specifically has to be, our method should be public, public node E right rotate or something, whatever you want to call it. Node E root, right? This is I cut myself with a knife yesterday on a bagel. So it was a really bad cut too, but it was worth it, I feel. But just once. Okay. I feel like I don't think it was worth it, but I certainly earned that bagel. Okay, there we go. That's a better way to put it. All right, so what we need to do is that we take in our root, and then we do our rotation stuff, all those steps. And here's the thing at the end, to make sure that basically that our tree doesn't get all out of whack or anything like that, we need to return root. And when we call rotate right, basically, we need, basically when we rotate a node, we have to let the parent of whoever we rotated know that their child changed. Right? Or in this case, we have to say that the root of the entire tree is now a different root, right? Which you might not do in the method, and that's fairly straightforward. You just simply say, you just do that outside in your main method. So what I want you to do is to essentially program a right rotation and submit it today. I will open up a assignment under quizzes for that and do that for, let's see how many points I've called it. 10 points. Do it for 10 points. All right, so just, yeah. So you'll want to use the binary tree, binarytree.java in the GitHub repo and implement a right rotation. Okay? And remember to return the new root of the subtree to the parent so the parent can set that to be the child, right? Just outside the method. You want to make sure that it gets returned. And so do that, submit it, and that's really all. And then I'll go through and check them off later. But it's not, I don't mean this to be hellish. It's really only, I mean, remember, these things are only kind of 4 lines long, but they require thinking. Right, to get to the GitHub repo, by the way, go to Pages. Go to the Pages, and I'll show you here.